Welcome back. Here's our second video for the day. This one we're going to introduce the Bolzano-Weierstrass theorem, but there's some other interesting ideas as well. The Bolzano-Weierstrass theorem is probably the first really big theorem that we'll do this semester. And you can kind of tell when theorems are big because they have some sort of name to them. So let's go through. But in order to do this, we'll talk about function or sequences that are increasing or decreasing, and kind of make sense of these things. Okay, so first we're going to talk about sequences that we call monotone, and really monotone is just a general term for sequences that either increase or decrease, either always increasing or always decreasing. So let's talk about what do we mean by increasing. So I'm going to say a sequence xn is increasing. Well, okay, we kind of know what we mean by increasing if I just draw a picture. If I were to ask you what's an increasing sequence, you would say a sequence where the values always get larger. And you would be exactly right. So xn is increasing if x1 is less than or equal to x2 for all, not x1 and x2, sorry, if x n plus 1 is less than, if x n is less than or equal to x n plus 1 for all natural numbers n. The basic idea is that each point is bigger than the point next to it. There is an interesting question, and if you ask this, good thing, and that is, why is this greater than or equal to and not just greater than? Well, you actually can choose either one. You can choose greater than or equal to or just greater than. But if you think about a sequence that looks, say, something like this. So what if our sequence, kind of comes up and then stays flat? So is this sequence increasing? It kind of feels increasing, right? Because the points are generally moving upward. But notice every second point doesn't change in height. We're going to include this as an increasing sequence, but some don't. But the reason why we do is most of our theorems, we want this equal sign whenever we prove things about increasing sequences or not. Okay, so because of this, we kind of have some terms. So I'm going to call this increasing. So books and authors that choose to not include the equal sign, they call this sequence, which is greater than or equal, they may call this non-decreasing. And then if they have the equal sign, they may call it strictly increasing. So let's just make a few notes here so that we can see that. So this is also called non-decreasing. In some ways, maybe that's a better definition, right? Because it gets at the fact that it never goes down. It always goes up or stays the same. But sometimes people have what they call strictly increasing in this book as well. So strictly increasing is the same theorem, except we use a less than, and we don't include that greater than in there. And then I'm not going to insult your intelligence by writing decreasing, because it's the same thing with the inequalities, the opposite direction. One other bit of notation that this textbook really likes, that I haven't really used a lot before, but I think I like it as well. It says xn, and then they'll put an up arrow a, and what that means is that xn is increasing and converges to A. So this means that it's an increasing sequence and converging to A at the same time. And that ends up being really nice, because once we have these two properties together, then we know a lot of things about the sequence. Okay, finally, the last thing that we need to introduce is this definition of monotone. And monotone is simply a sequence that's either increasing or decreasing. Now, that means it's either always increasing or always decreasing. Because notice, if you let it increase for a while and decrease for a while, well, every sequence does that. But monotone sequences are either sequences that always increase or always decrease. their sequence, they don't change direction at any point within their sequence. So a monotone sequence, a sequence that is either increasing or decreasing. And then I'll put always as kind of a side note. Because notice, when we say sequence is increasing, we're not saying it's increasing one time. We're saying it's increasing all the time throughout the entire range. Okay, so this brings us to our first big theorem. Maybe not big theorem, but our first theorem, and it's the monotone convergence theorem. And all it says is that if we have a sequence, that's monotone and bounded, so that means our sequence is bounded. Okay, here, hold on. Let's draw this a little bit better. So if we have a sequence, if it's bounded, that usually means there's some big M here and some little m here. And if it's monotone, that means it's either always going up or always going down. So let's assume our sequence is always going up. What do you notice has to happen as our sequence is going up? Well, it can't keep going up forever, right? Because that would break the fact that it was bounded. So what has to happen instead is that at some point here, it has to start leveling off. At some point, it's got to start leveling off, and we've got to have some sort of limit to this thing. So it must converge. Now, this picture suggests that it has to converge to that bounded point, but that's not necessarily the case. The sequence could also level off here and converge to some point much lower than whatever that bound is. But all we know is that it's got to converge somewhere, and hopefully the picture makes you realize that, oh yeah, it does have to converge. This is a necessary thing. How would we go about proving this? Well, the way we go about proving it is by taking the set of all these sequence points and then looking at the soup of that set, and that's the set that it converges to. So let's just let me just draw my picture over here, and we've got our sequence that comes upwards, and it, is bounded somehow. And so what I'm going to do is I'm going to start by letting E equal all these sequence points as a set, the set of xn, such that n is an integer. And what I'm going to notice about E is two things. It is non-empty, and it is bounded. Well, that's great. So if E is non-empty and bounded, then what does that mean? Then that means that it has a soup, a finite soup. Then S equal to the soup of E exists. Okay, so this is great. So E is non-empty and bounded, so it has a soup named S. Now, all I need to do is now prove that my sequence must converge to that soup. So basically what I've done is I've taken, thought of E, if we think of it on this axis, then E is the set that contains, let's do this a little bit better. So if I think of it on this axis, then E is all of these points. Oh, how many lines does an E have? All right, then E is all of those points. And then we've taken the soup, which we can see must be right here. And so if you look at our graph, it makes sense that your sequences should converge to the soup. All right, so now what's the next line in our proof? Well, we say let epsilon be greater than 0. And then we have this theorem from a long time ago that says that we know that if we subtract epsilon from the soup, we can find a point within it. This is the approximation theorem. The theorem seemed a little bit of a throwaway at the time that we did it, but this has ended up being really useful. So it's showed up for numerous theorems that we've seen so far. So let epsilon be greater than 0. Then we know that there exists some n such that S minus epsilon is less than x capital N is less than S. But we also know that these xn's are always getting bigger. So now we know that if n is bigger than capital N, then xn is greater than or equal to x capital N, because This is an increasing sequence. Well, notice I'm going to assume that it's increasing. If it was decreasing, we would do the exact same proof, except we would have less thans. So notice a decreasing proof would put a less than right here, and these would just change the directions of all these inequalities. This would be greater, greater, and less. Okay. All right. So if n is greater than n, then x is greater than capital Xn, since it's increasing. But therefore, s minus epsilon is less than x little n is less than or equal to s. But that just means that xn minus s is less than epsilon, which proves what we wanted to prove, because we wanted to prove that xn converges to s. So therefore our xn converges to whatever that sup value was. All right, so the monotonic convergence theorem, it makes a lot of sense. Hopefully this proof makes a little bit of sense also. This is a type of proof that it would be great if you all could, kind of internalize, and we could use as we go down the road. All right, we are ready now for the Bolzano-Weierstrass theorem, and this is a really big theorem. And what this says is that every bounded sequence has a convergent subsequence. So we don't know that every bounded sequence converges, by the way, and let's just give an example of that. So an example of that is the sequence sine of n, which we've seen before. And so sine of n, if I draw this as a graph, well, we know that it kind of follows this sine curve. So we know that it follows the sine curve, and so this sequence itself never converges. But what's important about the Bolzano-Weierstrass theorem is the Bolzano-Weierstrass theorem says that there must be a subsequence that converges. So let's just look at this and see what could I possibly do to make a subsequence. Well, one thing I might be able to do with the sine graph is just constantly take larger values. So what if I say, let's start with that value, and then maybe this value is a little bit bigger, so maybe this will be my x1, and maybe this will be my x2, and then that looks a little bit bigger, so we'll make that x3, and maybe that x4, and then we'll wait, and then somewhere down the road here, we'll eventually get a number either bigger or close to the same, and that sequence will be a sequence that converges to the number 1. So if I only include numbers that get larger, then I get a sequence that's getting closer and closer to 1. Sine is actually really interesting because we can make it converge to really anything that we want. That's kind of unusual. Usually, you're finding a specific subsequence that converges to. But what this says is that if it's bounded, then it has a convergent subsequence. All right, we need a theorem before we get into this, because we can't prove this theorem. Well, maybe we can, but the way we're going to do this proof is we're going to use the nested interval property. We could call this a lemma, but I would call this more than a lemma, because this is a property. Usually a lemma is something you prove for your specific theorem, but you don't really use it outside of your own theorem. This is a more important property because it's going to be used for several theorems here and in other courses. So this is a pretty common property itself. You could call it a lemma. And in fact, there have been times when a mathematician proved a lemma to finish a theorem, and it ended up that the lemma was a lot more important than the theorem is. But okay, the nested interval property basically says if you have a nested sequence of non-empty closed bounded intervals. So let's say, what in the world is this talking about? Well, intervals, closed bounded intervals, are really just intervals that look like this, that have our endpoints on them. They include our ends. Okay, and a nested interval, so this might be I1, would be that big, bounded interval. But then a nested interval is an interval inside of it. Oh, let's call that I1. And so inside of that, we might have another interval. And a nested interval just means that each endpoint, it could be actually at the same spot, but it's not further out. So maybe that interval right here will be our interval I2, and then maybe we'll create another one. We could even use like the exact same endpoint there, and then come here, and then that one could be I3, etc. And so we would nest an interval inside of that and nest an interval inside of that. Okay, and then eventually what you notice, so the point is that when we're done with this, we have some sort of interval that's left over in the middle. And this left over in the middle part can't be empty. So we can't be left with nothing in the middle. There must be something in the middle of all these intervals that are nested inside of each other. Well, here's how we're going to prove this. The way we're going to prove this is just referring to each of these intervals as with the notation AN, BN. So we'll just let our interval IN be AN, BN. So that very first interval that I showed would have gone from A1 to B1, and the second interval A2 to B2, etc. Then what I will notice, if I draw that picture again, is we have A1 and B1, and then our next interval is here, A2, B2, and then our next interval is here, A3, B3, ... So they kind of continue in. And what I notice is that my sequence AN is two things. Well, it is increasing because the A's always go in one direction. And not only is it increasing, but it's also bounded because each point has to be smaller than the B's. Because if I ever got an A larger than any of the B values, then my intersection, then they wouldn't be nested anymore because they wouldn't have fallen inside of the sequences that I'm talking about. So it's increasing and bounded. So what does that mean? So that means that that sequence must converge to some letter A. Similarly, our sequences BN must converge to B, and not only that, because all of our ANs are always smaller than all of our BNs, we know that A must be less than B. So therefore, the intersection, and this is the infinite intersection that you all probably remember from transitions, and it brought you great joy in that class, and it will bring you joy every time that you see it from now on. So therefore, the intersection of all these things, the intersection of all the INs over all the natural numbers, is simply that interval AB. And so this is non-empty. And this is non-empty, which proves our theorem. However, I want to make an important observation. It is possible, right? So it's possible. Oh, uh-oh. All right. It is possible that A equals B is possible. And what would it mean if A equals B? Well, if A equals B, all that would mean is that this sequence is A, but that is just a single point A. Okay, so it's definitely possible that you have only one point when you're all done with these. I want to make a few observations before I move on and kind of show how this proves the Bolzano-Weierstrass theorem. So my first observation is that this idea of being closed matters, right? So our sequences must be closed. Why is that? Well, let's just think about the example here, 0 and 1 over n. What happens when I intersect all of these? Well, if I intersect all of those, then these are open intervals. And so if I intersect a bunch of open intervals, well, notice this actually is the empty set because there's no element that can fit inside of here. If you take any positive real number, right, any x that's greater than 0 will eventually not be in one of those. So it is not, not larger. There'll eventually be a 1 over n smaller than that. So it'll fail. Okay, so they must be closed, but not only that, they must also be bounded. And so if you want to think about an example for not bounded, well, we could do n to infinity. This is a closed set. If you're asking why that's closed, we'll talk about that kind of towards the end of the semester. If you include an infinity, the infinity side, even though we use the open bracket, that kind of has both an open and closed connotation, because closed kind of asks the question of, does it include every point up to infinity? And the answer is yes. Every point, including, as large as you get, is included, which makes it closed. But also open is kind of the idea of, well, does infinity in it? Well, it isn't. So this kind of is a bit of a paradox. But that being said, there's a more precise way to go about this, and we will talk about that in just a little bit in the semester. But this is considered closed. However, if we intersect all of those, then what happens? Well, that is also the empty set, because any, for any x and r, you eventually will get, you eventually find n bigger than the x. So up here, you find a 1 over n smaller than that x. So what's important here is that this nested interval property must be closed bounded intervals. If they're not closed and bounded, then this is going to fail. Okay, it's time. It's time for the Bolzano-Weierstrass theorem. And I'm going to not prove this theorem in words. I'm going to prove this theorem in pictures, and then let you all kind of read the proof in the book and see how the words work out. One quick note, this big theorem, along with others like it, I'm going to ask you all this semester for the final exam. We're doing presentations on our exams. I'm going to ask you on the final exam to pick one big theorem from the semester, and I'm making a list. There's a Wikipedia page on the on our class website, and I'm going to ask you all to sign up for one major theorem to do a presentation of, and this is one of them. In fact, this one's significant enough. I put a little star by it, and I'll give whoever chooses the Bolzano-Weierstrass theorem some bonus points, because there's a lot going on here. But as you're going through the semester, and as we're talking about these major theorems, kind of think to yourself, ooh, that was one I really understand. I found it interesting. I'm willing to do a presentation over it. Okay, so the Bolzano-Weierstrass theorem says every bounded sequence of real numbers has a convergent subsequence. Now what we're going to do here is, if we think about our sequence, kind of, being bounded above by m and bounded below by negative m, then, our sequence might do different things as we go through here. Well, what we're going to do is we're going to basically take this interval m and split it up into halves. So we're going to split it up into a half like this, and we're going to look at each section, and we're going to ask our question: how many points are in each half? How many points? Well, the answer is one of the two sections must be infinite. It could be that they're both infinite. And so the question is this side have an infinite number of points? Or does this side have an infinite number of points? Or do both sides? Well, what we're going to say is, we're going to say how many points? Well, we're going to choose a side with an infinite number of points. Notice one of them must have an infinite number of points, because if they both had a finite number, well, then we would be in a situation where there's only, if they only had a finite number, then we'd be in a situation where, then we'd be in a situation where we have only a finite number of points in our entire sequence, right? You can't have a sequence with an infinite number of points, split it in half, and get two finite numbers. Okay, so how many points? There'll be only a finite number of points. So once we've done that, we will choose the side with an infinite number of points. Let's just assume, for our sake, that it is this half right here is the infinite half. And then what we'll do is we'll pick a point in that sequence, pick a point anywhere in that section, and call it x1. And so we'll call that point x1. But then what we're going to do is we're going to divide that section in half. And then again, we're going to pick our infinite points. All right, and then we go, okay, well, which side has infinite points? Well, let's say this bottom one has the infinite points. Okay, and then we'll go pick our x2, the bigger than x1 in that section. So, I don't know, maybe that one. There we go. So there's an x2. And then we'll divide that section in half. And then we'll say which of those two sections, here we'll call that the infinite one. And then we'll say which of those two sections. And let's say the upper one has an infinite number. So we'll pick one in that section, which has, and we'll call that point x3. And what you see is happening is that we are taking our sequence, and I'm going to clear my page again so that we can see it. So what you see is happening is we're taking our sequence, and we're taking our whole range, and first we're cutting it in half, then we're cutting that in half, then we're cutting that in half, that in half, that in half, that in half, and we're kind of continuing to cut it in half. And what you notice is that eventually you end up with some situation where for any epsilon you want, then we let epsilon be greater than 0, then eventually these sections get smaller than epsilon. So eventually you get to where there's some section here that's smaller than epsilon, and when I draw that out, I have an infinite number of points, and so that means, and so every point after whatever that point is, so say this is the nth section, say this is section n, then all I have to do is come over here, and take whatever I chose for that xn point, my x capital N point, and I just cut it off right there. And notice every point after that is guaranteed to be less than epsilon within that section. And so what we've done is we've made our sections smaller and smaller and smaller by dividing our interval smaller and smaller each time. But each section has an infinite number of points. Now, what you'll notice is that what we're doing is we're making a collection of nested intervals. So what you'll notice is that this gives us a collection of nested intervals. And so we're kind of back to this nested interval problem again, except we're actually with the nested interval problem where the top and the bottom intervals become infinitely close to each other. And so at the end, we end up with an interval that's just a single point, and that single point is the limit of our sequence. Okay, once again, I'm not going to work out the details of this, but hopefully this proof makes a little bit of sense of how you would construct it. I'd encourage you to read the book's proof. The book's proof has a lot going on. But it's understandable once you kind of have the big picture of the problem in your mind. All right, so this is the Bolzano-Weierstrass theorem. It's super useful. So in fact, there'll be multiple times this semester when what we do is we start by creating a sequence that's bounded and convergent, and then we have, or is bounded, that's bounded, and then we know we can take a convergent subsequence. And once you have one subsequence that's convergent, you can use that subsequence to learn all sorts of other stuff about the part or the problem that you're working with. So there you go. That ends this lesson, and these are the things that we're going to talk about in class on Monday. And I look forward to